Here is a combined summary of the 4 pages. The proposed approach to image restoration and enhancement combines wavelets with multifractal priors within a Bayesian framework, extending previous Fourier space methods to the wavelet domain. This leverages the advantages of wavelet analysis, which captures local image properties more effectively than Fourier analysis, and benefits from the extensive literature on wavelet shrinkage methods. Empirical Bayes methods are employed to incorporate multifractal properties, enhancing the recovery of textural characteristics in images, particularly in medical imaging contexts where differentiating between healthy and diseased tissues is crucial. Performing image enhancement in the wavelet space retains computational efficiency, reducing the problem from a large multivariate optimization to a series of smaller, independent univariate optimizations. This facilitates the practical application of Bayesian image restoration techniques, which have historically been computationally intensive. The use of wavelets allows for better adaptation to local image properties and capitalizes on the extensive research in wavelet shrinkage methods. Previous pixel-based Bayesian image restoration methods have focused on computational intensity. The author's approach involves moving the posterior distribution calculation to Fourier space, treating modes as independent, and reducing the problem to a set of single-variable optimizations. This produces restored images comparable to standard Bayesian methods. Parameter functions, representing prior information about the image in the orthogonal space, are generated using a power law for the prior mean in Fourier space, with variance proportional to the mean. This implementation provides a smoothing prior, giving more weight to the likelihood distribution at high spatial frequencies and the prior at low frequencies. Extending this method to the wavelet domain, focusing on multifractal priors and wavelet shrinkage for generating parameter functions, has shown promising results. Assuming a decreasing power law for finer wavelet scales results in effective image restoration. The flexibility of the methods allows for incorporating shrinkage methods and comparing with current state-of-the-art wavelet shrinkage-based restoration methods. The ultimate goal is to enhance MRI perfusion images using parameter functions generated from co-registered PET images, leveraging the information content across multiple PET images to enhance the resolution of the restored perfusion images. In the context of image restoration, the choice of likelihood and prior distributions in Bayesian imaging in orthogonal space significantly impacts the algorithm's effectiveness. A Gaussian prior distribution leads to a Gaussian posterior and a simple formula for the map estimate, as shown in equation 1. The authors emphasize the potential benefits of combining Bayesian image analysis in wavelet space with wavelet shrinkage and multifractal approximation methods. They propose using wavelet shrinkage properties to capitalize on the sparse representation of typical signals in the wavelet domain, assuming that most coefficient values less than a predetermined threshold represent noise and can be zeroed, while those greater than the threshold represent signal and should shrink by some amount, also specified by the threshold. The authors suggest employing the thresholds proposed in 6 and 9 for this purpose. In multifractal analysis, the Holder exponent is introduced as a measure of fractal or multifractal behavior, characterizing the local regularity of a function. It is defined as the supremum over all values for which the Holder continuity condition holds, with a straightforward linear regression method being used to estimate the Holder exponent at finer scales. This method involves extending a linear fit of log 2, W, U, S, versus S to small s, where W, U, S, represents wavelet coefficients, and S represents scale. The authors also discuss the use of a threshold similar to that for Bayes shrink, which is determined by the scale at which the noise amplitude becomes comparable to the signal amplitude. For scales below this critical scale, the proposed use of the mean as a prior parameter function is specified. This approach aims to enhance the ability of the restoration algorithm to preserve textural properties by utilizing the scaling behavior of multifractal patterns that effectively model textural qualities. The method proposed in 9 estimates finer scale multifractal estimates using more specific local information, such as modulus maximum methods and wavelet leader methods, but the straightforward linear regression method was found to be effective for generating prior parameter functions. The research integrates Bayes shrink and multifractal estimation methods into a Bayesian restoration algorithm in the wavelet domain, emphasizing the importance of retaining smaller values at fine scales to indicate noise presence. The prior mean and variance functions, defined in equations 8 and 9, are applied at scales above the critical scale, mimicking Bayes' shrink and multifractal estimates. The critical scale is determined based on image resolution, set as the finest wavelet scale in the examples. The algorithm involves estimating Holder exponents for all indices in wavelet space that are finer than the critical scale, followed by the use of conjugate Gaussian formula and prior parameter functions to obtain the map estimate coefficients. This process is divided into two steps, one for scales coarser than the critical scale, implementing Bayes' shrink, and another for scales that are finer than the critical scale, implementing multifractal estimation. The proposed WIMP method extends Bayesian image processing in Fourier space to orthogonal representations, specifically focusing on wavelet bases, enabling restoration of local image properties. WIMP uses a two-stage approach, first performing a coarse-grained analysis with Bayes' shrink to estimate noise and image variances, followed by a fine-grained analysis that incorporates multifractal properties, utilizing the Holder exponent to adjust wavelet coefficient shrinkage thresholds. Performance comparisons with Bayes' shrink and Vicious shrink demonstrate WIMP's strength in restoring textural properties in images, effectively characterizing irregularity and regularity. WIMP outperforms shrinkage algorithms in edge and smooth area restoration, reducing noise and extrapolating smooth regions. The results suggest that WIMP's ability to incorporate insights from wavelet shrinkage algorithms and wavelet-based multifractal analysis makes it a promising tool for image restoration tasks. The research paper introduces a novel Bayesian image restoration framework, WIMP, which combines insights from wavelet shrinkage and multifractal estimation methods. It demonstrates the effectiveness of WIMP in characterizing image texture, outperforming traditional wavelet shrinkage methods. However, it notes that WIMP's edge detection capabilities are somewhat limited, an issue that can be mitigated by incorporating Bayes' shrink at coarse scales. Future extensions should focus on enhancing edge detection without compromising texture recovery. Empirical methods for determining prior parameter functions are crucial, especially in imaging studies where local features are key. The paper also suggests exploring robust Holder exponent estimates and different wavelet bases, favoring the Gaussian conjugate prior for computational efficacy. The research was supported by the National Institute of Biomedical Imaging and Bioengineering. In another section, the paper emphasizes the importance of fractal and multifractal analysis in understanding complex systems, referencing seminal works in the field. Wavelet denoising techniques are discussed, highlighting the significance of local regularity information. The relevance of Bayesian data analysis to the research is detailed, followed by a technical overview of mathematical concepts such as the Riccian distribution, multifractal formalism, and non-concave entropies. The importance of Python libraries like NumPy, Matplotlib, and scikit-image for efficient numerical computation and data visualization is also addressed. The discussion concludes with the K-Bayes reconstruction method for perfusion MRI and its application in medical imaging. Key terms, concepts, and methodologies are explained with precision, emphasizing novel ideas and significant findings throughout the paper. Here is the combined summary of the 4 pages. The research applies Bayesian methods to image denoising, leveraging multifractal models for coefficient estimation. Specifically, it proposes Holder exponent-based multifractal estimates, utilizing the map estimate formula, where the scale and location-dependent value serves as both a threshold for coefficient estimation and the estimated coefficient value. This approach, termed WIMP, is compared to existing methods, namely Bayes' shrink and Vicious shrink, through simulations, as illustrated in Figure 3. The results demonstrate the efficacy of WIMP in restoring images with added noise, particularly in complex backgrounds, showcasing its ability to capture the varying smoothness of image components. The Hurst exponent in the fractional Brownian motion background is emphasized as crucial for accurate simulations. The study further investigates the comparison of different shrinkage algorithms for image denoising, focusing on Bayes' shrink, Vicious shrink, and WIMP. A visual comparison is presented in Figure 4, depicting the restoration of the standard cameraman image with added noise using these algorithms. This figure highlights the performance differences between the algorithms, with WIMP exhibiting improved denoising capabilities. The multifractal model's adaptability to local image features is identified as a key advantage, enabling more effective noise suppression. The research contributes to the development of advanced image denoising techniques by integrating Bayesian methods with multifractal models, providing a promising approach for tackling complex image denoising challenges.